All right, so let's try 2D integration. And I'm writing 2D integration, yeah? But what do I really mean?
It's 3D.
Yeah, really, I mean I'm going to get a three-dimensional thing, right? Okay, so I've got some surface, right? It's going to look like this. Okay, everybody good with my surface? All right. Now, what I would like to do is I would like to take some little square out here, or rectangle out here, and I'm going to say that's A to B in the, which axis is that? X-axis. Okay. Good. And that's going to feel a lot like the integration we know and love, right? Okay, and then on the other side here, I'm going to add a C and a D. And those are going to be on the y-axis. Okay. And now what am I going to look for when I try to do some kind of integration-y thing? Yeah, like before I was doing area under the curve, right? So here when I've got a function like this is a surface, right? F of x and y. Yeah, so I'm going to get a volume under the surface, right? And that volume, right, is if you follow this thing up, and this guy up, and this guy up, and this guy up, right? You're going to get some other little piece of surface here. And you're going to be finding the volume of that kind of off trapezoid-y funky thing, right? Cool. So I'm looking for the volume of this kind of off prism. So how am I going to do that?
Probably the change in x and the change in y.
Little bits of it, slices.
Yeah, I'm going to make little bits of slices, right? You guys all see that? Okay, so first things first, I'm just going to say, all right, I can't think this way, right? I'm going to have a hard time drawing this picture. So I'm just going to draw the bottom of that blue thing. So this is A and B and C and D. Okay? So I've got Y's that way, X's this way. And so I took that blue thing and I pulled it over here. Are you good with that?
Sure.
Okay, now I'm going to cut this up into some pieces, right? Okay, so let's just cut it up into pieces. Okay, that's going to be impossible, right? To draw. So I'm going to cut it into just a few. But the idea, right, is that I'm going to cut it into lots. So I'm going to cut that side into 3 pieces, and I'm going to cut the Y's into 4.
Just because you feel like it.
It doesn't really matter, right? I'm going to cut them both into lots and lots of pieces in practice, right? Okay, how about this? How wide is each little x slice? Probably delta x seems like a good idea. Okay, so there's a delta x, there's a delta x, there's a delta x. All right. These guys are probably delta y's, right? Okay, and now if I complete this chunking process, right? I'm going to have a whole bunch of bases. You guys all see that? So those bases in here look like this. You guys see that? And now I'm wondering, how am I going to approximate the volume above that thing?
Took the value of the function.
Yeah, good. Okay, so volume of, I'm going to call this the ith base here, right? Just pick one at random. So volume of ith base. How do you get there? O. Over. Volume over ith base.
Delta Y. times
Sure,
delta
perfect.
X.
So the base itself is delta x, delta y, right?
Times the value, x1,
Yeah, times some function value, right?
x y, y star.
Okay, now this is going to get weird because I just picked that at random as the ith one, right? I should probably be a touch more organized than that. So how can I make my life a little more organized?
Starting at like a corner or something?
Yeah, so I really, to call this the ith one, I need an organizational scheme for how to count, right? That's going to get weird and we'd have to agree. So I'm going to slim that down a little bit into, we're going to call these by 2 coordinates, right?
Okay,
One for the x and one for the y. You guys cool with that?
sure.
Okay, so in general, I'm not going to do ith bases. I'm going to do like,
I plus G.
yeah, ij based, right? You guys all see that?
Yeah.
And then I can just do, well, the first coordinate's the x and the second coordinate's the y, right? Okay, is that going to change anything about this? I'm going to say over the ij base. What's that going to change? Anything? Yeah, it should be x sub I, y sub j, right? You guys see that? Okay, now what? Well, that gets me the volume over one of these, right?
So,
Do like A,
we need two summations.
Okay, so I need a sum, right? So if I do one sum,
It would be for I equals 0 to n, and then the second sum would be j equals 0 to n.
okay?
The reason why you did it backwards.
No, not really. So here I chose, right, to sum the x's across first, and then go up one in the y and do the x's across again. Does it matter?
no.
No, not at all, right? So you could certainly switch these two things. That would also be fine. Cool?
So then, after that, you have like one f of that.
Hang on. So this should be the total volume, right?
Yeah.
Okay, so the total volume should be the double sum of what?
Fx of y.
Okay, f x I star y j star.
And then delta x of y.
Okay. And we should note, right, that this one was the x's, that's the x's, those two go together, right? This one's the y's, this one's the y's, those two go together.
And if the change of x was 1 and the change of y was 2, would you change the j to 2?
The change in, so it depends on how far you're trying to go.
Okay.
Like in this case, I have 3 x slices,
Yeah.
right? So my n, my x number would be 3. And my m, my y number, would be 4, right? They don't have to be the same is the only thing going here. Cool? All right, so if you were going to write this as a volume actually equals, what's the set of symbols you would write?
Limit x approaches 0.
Is that what you call it too?
Double integral, yeah.
One's A to B, one's C to D.
Okay, which one goes where?
Well,
It'd be C to D.
Yeah, good. It's,
So-
so 1, it probably doesn't matter most of the time. And 2, whichever order you wrote the Riemann sum down in. You guys see that?
okay.
So here on the inside I have x's.
Uh-huh.
So I'm going to do A to B on the inside. Cool.
Yeah.
And that's going to be f of what?
X and Y.
X and y, right? And I'm going to do which one first?
Delta. DX.
Delta x turns into a dx, right?
dy.
And the other one I'm going to do c to d, and that's going to be dy. So what did I do to get from the approximately equals to the integral signs?
And X and Y goes to 0.
Yeah. So that's really the limit as delta y goes to 0, the limit delta x goes to 0 of these two sums, right?
And then also m and n going to infinity.
Yeah, it's the same thing as m and n going to infinity, right? And I really should say that here because my delta x's, right, and my delta y's, those certainly depend on m and n. Right? In fact, they're exactly a function of m and n. They're, so, anybody tell me? Delta x is
B minus a over n.
b minus a over n, and delta y is
C.
D minus C.
D minus C over N.
d minus c over m. You all might note, right, this is a one-dimensional displacement vector. Right, this is the terminal point minus the initial point. Crazy, right? All right, so we take these two limits of the sum of the stuff we were just talking about, right? And that gets us to this notation.
Yeah.
How do I execute this notation? Like,
Inside. You do. Yeah.
you do the inside first. So do the integral dx. How do you integrate dx when there's y's kicking around?
Partial.
Yeah, it works exactly like partial integration does. Is there anything new here really at all?
So I'm just treating my constants.
Yeah, you must treat the other variable like a constant.
So it's pretty much like a composition sort of thing?
Yeah, it's exactly composition of two functions of functions.
Okay.
Yeah, there's this derivative thing and this integral thing, right? So if you drop the a and b, c and d, right?
Yeah.
That's a thing that takes a function and turns it into another function.
Okay.
Right, it's called a functor. So this is, yeah, a composition of two functors. Great. Whatever. Yeah, really. Okay, so what I want you to take from this is that the Riemann integration picture looks exactly the same, right?
Yeah.
Calculating volumes, you need to approximate, then you take a limit, sending the chunk size to 0. When can I do this to a function f?
Continuous.
Oh, right, not differentiable.
Yeah, continuous, I don't need differentiable.
Yeah.
And in fact, I don't even need that continuous.
That continuous.
Yeah, like jump discontinuities, this thing will be fine. Those sheer cliff discontinuities, this thing will be fine.
So like,
Problems that might be more annoying are like when you make von Koch snowflakes or something, then this will break.
so do you mean like continuous from both directions?
It would be enough if both the one-sided limits existed.
Okay.
We're gonna just, everything we do is gonna be continuous, but I want you to know that assumption's a little bit robust, right? You can get away without that. Because of course, right, we found spots in topography, right, walking around in the boulders, where there wasn't limits, right? Where three-dimensional functions weren't continuous, right? Did they still have a volume underneath them?
Yeah.
Yeah, and I mean, we could even dig them out and see what it is, right? So, good, cool. If you assume f's continuous, this thing works. Check.
Yeah.
Okay. That's what I want you to have for starters.